So in this short video we will discuss about the lumped capacitance. This lumped capacitance is used when we deal with problems involving transient heat transfer or unsteady state heat transfer. So I will give an example in order to explain this scenario. So consider that I have this metallic ball. This is a metallic ball, metallic sphere. So this is a metallic sphere. Now this metallic sphere is at a temperature Ti. So we are assuming that this metallic sphere is at a temperature Ti initially. Now this is a tank which contains water. So let the temperature of this water be T infinity. So now if I put this ball or if I put this metallic sphere inside this tank, what do you think will happen? If the temperature of the metallic sphere Ti, if the temperature of the metallic sphere Ti is greater than T infinity, so it is obvious that the metallic sphere will start to. So after I have put this metallic sphere inside this tank, the sphere will start to lose heat to the ambient surrounding, and the temperature will be somewhat less than this temperature Ti, and this T will obviously be a function of time. So if someone asks that after 2 minutes of putting this sphere inside this tank, what will be the temperature? After 2 minutes, after T equals to 2 minutes of putting this sphere inside this tank, what will be the temperature? Then how will we answer these type of questions? So to solve these type of problems, what we use is the lumped capacitance model, So I will show the equation which deals with the lumped capacitance model. It shows that T minus T infinity divided by Ti minus T infinity equals to e power minus h ast divided by rho v Cp. I will explain each of the terms individually, do not worry, but see what these temperatures are. This T is the temperature of the sphere when it is put inside the tank, inside the water tank. Now remember that this T is obviously a function of time. This temperature will obviously be a function of time. The longer I keep it inside the tank, the more it loses heat and the temperature decreases more. This T infinity is the temperature of the water. Ti, what is this Ti? Ti is the initial temperature of the sphere. It is the initial temperature of the sphere, and this T infinity is again this T infinity. Now what are these terms? This H is, this first term H is the heat transfer coefficient. Heat transfer coefficient. It will obviously be mentioned to you in the problem. What is this As? As is simply the area of the sphere. As is the area of the sphere. So next is this T is nothing but the time, so I am not writing it. What is this rho? Rho is the density of the sphere, density of the sphere. So density of the sphere material, So if it is of iron, then the density will be of that of iron. If this sphere is made of copper, then the density will be of the copper. So next what we have is, after rho what we have is V. V is the volume of the sphere. Let me write it down. V is the volume of the sphere. Volume of the sphere. And lastly what we have is Cp. Cp is the specific heat capacity of the material. Specific heat capacity of the spherical of the material, that is of the sphere material. Of course, if it is made of copper, then it will be a specific heat of the copper. If it is made of iron, then it will be the specific heat capacity of iron. Next what we will do is, so now we can write this equation in another form. Let me write it over here itself. This T minus T infinity can be written as theta, and Ti minus T infinity, that is this term, can be written as theta I. So what I can write is theta by theta I equals to e power minus T by tau. This is another way of writing this entire thing, where the value of this tau will be rho v Cp divided by h As. This will be the value of this tau. Now if we plot this, let me write this down over here. Theta by theta I equals to e power minus T by tau, where the value of this tau equals to, what is the value of this tau? rho Vcp by HAS, rho Vcp by HAS. This is another way of writing this. So this tau can be divided into two parts, rho Vcp into 1 by HAS. So both of these has a significance. This is the resistance, and this is the capacitance. So what is this resistance? This resistance term 1 by HAS gives the resistance. So this resistance term gives the resistance for convection, that is convection from sphere to the surrounding water. That is the resistance for convection of heat. Now next is this capacitance. What is this capacitance? This is the capacitance for the solid to store heat. Capacitance of the solid to store heat. So this is what this rho Vcp signifies, and 1 by HAS gives the resistance term for convection. So now what is this tau? This tau can be written as a time constant. This is a time constant. So now we can plot. So now we can draw a plot between this theta by theta I and this time. So if I plot this, so this is the graph that we will use. So in the y-axis we will take theta by theta I, and in the x-axis I will take time. Now let this be 1. So this is the 1. Now from at t equals to 0, obviously theta by theta I will be 1. At time equals to 0, theta by theta I will be 1. So the graph will start from 1 and it will be like this. So I am writing the relation over here, theta by theta I e power minus t by tau. So this will be the series of curves that we will obtain, and this is the direction of increasing tau increasing. So for low values of tau, this will be the curve. And if I increase the tau, the time constant will be the curve. So as I keep on increasing the tau, the curve shifts towards the upper end. So next what we will do is we will discuss certain assumptions. On which these lumped capacitance are valid. So I will write those assumptions. So the first important assumption for the lumped capacitance model is the Biot number must be less than 0.1. That is, the Biot number is HL by K, where H is the heat transfer coefficient, L is the characteristic length, and this K is the thermal conductivity, thermal conductivity of the solid, of course. So this must be less than 0.1. Only if this satisfies, we can use all of these equations that we have derived. That is this equation. Only if this Biot number is less than 0.1, then only we can use this lumped capacitance. So we can write this Biot number in another way. We can write this as Biot number equals to HL by K. So this is what we had. So we can also write this as H into A. I am multiplying with the surface area of the sphere over here into L by Ka, and I am also dividing with the surface area of the sphere. So this I can write as L by Kas divided by 1 by HAS. So I hope you understand that both of these are similar things. I have not altered the expression, I have only written it in a different way. So what does this term indicates? This term is the ratio of resistance due to conduction, and in the denominator what we have is resistance to convection. So now what we can say is, because Biot number should be less than 0.1 to have the lumped capacitance model, also we can say that the resistance to convection should be higher than the resistance to conduction if we want to apply the lumped capacitance. So this is the another thing. Let me write this down. Another way of writing this assumption, that is the Biot number must be less than 0.1 is resistance to convection. Resistance to convection must be higher than the resistance to conduction. So if this is also true, then we can apply the lumped capacitance model. That is all these discussions that we have done. So there is another thing that I would like to say over here. Another important thing that we can write here is the temperature profile within the solid should be uniform. This is another assumptions you can say, but all of these are derived from this same thing, that is the Biot number should be less than 0.1. Now from altering this expression we can derive these two things further, that the resistance to convection must be higher than the resistance to conduction and the temperature profile within the solid should be uniform. If this satisfies, then the assumptions are true, then we can use this lumped capacitance model. The basic assumption is that the Biot number should be less than 0.1. Hence this too follows from that expression, that if Biot number is less than 0.1, then obviously the resistance to convection must be higher than the resistance to conduction and the temperature profile within the solid, that is this iron or the metallic sphere, should be uniform. The temperature gradient should not exist. That is, if at this point the temperature is T1, then at this point this cannot be T2. This cannot occur. It should be same or uniform. The temperature should be uniform within the sphere. So that is what I have written here. The temperature profile within the solid should be uniform. So the only thing that you keep to notice is that the Biot number must be less than 0.1. These two follows from that same assumptions. These two are the follow-ups from this same assumptions. So now that we have talked a lot about all this, let's try to use this equation. Let's try to use this formula, this one, and solve a important problem. So now we will solve an important problem. So we will try to solve this problem. The steel sphere of radius 0.1 meter at 400 Kelvin is immersed in an oil at 300 Kelvin. If the center of the sphere reaches 350 Kelvin in 20 minutes, how long will it take for a 0.05 meter steel sphere to reach the same temperature under identical conditions? So firstly, in order to apply the lumped capacitance, what we should know is the assumption should be correct. That is, we will assume that the Biot number is less than 0.1. So nothing is mentioned in this question, so we have to assume that the Biot number is less than 0.1. Now if this is true, then what this follows is, if Biot number is less than 0.1, obviously the resistance due to convection should be much higher than the resistance due to conduction, and also the temperature within the sphere should be uniform. The temperature profile within the sphere should be uniform. So with this set, we can start solving this problem. The equation that we had is T minus T infinity divided by Ti minus T infinity equals to e power minus HAS T by rho V Cp. This is the equation that we had. Now what is mentioned here is a steel sphere of radius 0.1 meter at 400 Kelvin. So Ti is 400. So we can start putting the numbers in. This will be 400. Now is immersed in an oil at 300. Temperature of the oil is given as 300 Kelvin. So this will be 300, this will be 300. Now if the center of the sphere reaches 350 Kelvin in 20 minutes, so the time is given and this temperature at the time 20 minutes is 350 Kelvin. It is mentioned over here. So this is equal to e power. So what they have only given here is H is not given, Cp is not given. So and rho is also not given. So I will put those terms in the side, H by rho Cp. This I will put on the side into T divided by V, and also I have this As. So for a sphere, what is the ratio of, for a sphere, what is this As by V? As by V, area of the sphere is pi 4 pi r square and the volume of the sphere is 4 by 3 pi r cube. So pi gets cancelled. What this becomes is 3 by r. So here instead of this As by V, I will replace it with 3 by r. So this term is constant. So what I get is, so what they have said is that under identical conditions, so this H by rho Cp will be same. So we will take this as some constant A. I will take this as a constant A. So what we get here is 50 by 100. 50 by 100 is e power minus A times 3T by R. So what is the value of T? The value of T is 20 minutes in this case, and the value of R is 0.1 meter. So what we get is e power minus A into 3 into what will be T? T will be nothing but 20 minutes, and what is R? R is 0.1 meter. So this is equal to 50 by 100. So this is my first equation. Now what they have said is, under identical conditions, how long will it take for a 0.05 meter steel sphere to reach the same temperature? So they have just reduced the radius. So everything on this side will be same, the temperatures will be same over here. So I will directly write 50 by 100 for the next case. This will be equal to e power minus A. A will be same because this H by rho Cp will not change for the second case. What will change is this T and R. The time required and the radius will change. So time required I don't know. This will be 3. And what is the radius? The radius this time is 0.05. So from these two equations, from this 1 and 2, it is easily noticeable that I can simply equate both of these terms, because everything is same. I can simply compare. So T into 3 by 0.05. I am comparing this term with this term. I don't have to take log and all because it is a simple calculation. So it equals to 3 into 20 by 0.1. So the value of this T can be easily find out. 3 gets cancelled. What we have is T equals to 20 into 0.05 divided by 0.1. This gets cancelled. This is 100. This gets cancelled into 10. So what I get is these two zeros will cancel with those two. So what I get is 5 2s are 10 minutes. So the answer is the time required for the new small sphere will be 10 minutes. 10 minutes to reach this 350 Kelvin in 350 Kelvin. It will take 10 minutes. Before, the 0.1 meter sphere took 20 minutes, but now the 0.05 meter sphere will take 10 minutes. So this was all. About this video. What we had done is we had seen what lumped capacitance is, and we had seen this expression. This expression is very important. Also, what we had done is we had seen assumptions that are needed for using this lumped capacitance. These are very important. The first important thing is this expression. This expression is very important and a very important takeaway from this video. And the second thing are these assumptions that Biot number must be less than 0.1 in order to use this lumped capacitance. So if I have this Biot number less than 0.1, then the things which follow are the resistance to convection must be higher than the resistance to conduction. If Biot number is less than 0.1, then this is also true, and also the temperature profile within the solid should be uniform. This is also true. And lastly, we had also solved the problem. So this was all about this video. Thank you.